Good evening, everyone. Thank you for coming. Thank you. And welcome to the Cahill Center for Astronomy and Astrophysics. Thank you so much for coming. I know that you're all eager to hear about the South Pole, and I don't want to delay that, but I first have to make just a few quick announcements. For those of you who have not been, whose first time is it to this event? Oh, quite a lot of people. Okay, so let me just explain how this is going to work. So the talk, Abby's talk, is going to last about 30 minutes, and then after that, we're going to have events in 2 different spaces. In this space, we're going to have a panel of experts to answer whatever questions, burning questions you may have about astronomy. And outside, out the back, we're going to have some telescopes set up where you can see the Orion Nebula, the Moon, and Jupiter to start, and then we'll sort of see how the night goes. But the weather looks great, so we should at least be able to see those 3 objects. Right. This is all going to be very informal, and so after the lecture is over, you're welcome to come here, go out there, and come back and forth as you like. We have various handouts and flyers on the way into the auditorium, as you may have seen, so if you haven't already picked those up, please feel free. After the lecture, if you need any help getting anywhere, have any questions, there are volunteers, we all have badges, so just feel free to stop us and ask. And finally, please come back for our lecture next month when Jackie is going to be telling us about the history of air on Venus, the Earth, and Mars. Okay, so with that, I'd like to introduce Abby Kreitz, our great speaker for this evening. Abby was an undergraduate here at Caltech, but she did her PhD at the University of Chicago. But apparently she couldn't stay away because now she's back for a postdoc. She builds cameras for telescopes, and tonight she's going to be telling us about her experiences doing that for a telescope out the South Pole. So with that, take it away.
Okay, can everyone hear me okay? Awesome. Yeah, so I'm going to talk about astronomy at the bottom of the Earth, some telescopes at the South Pole, and this is pretty informal too, so feel free to interrupt me if you have questions. That's totally fine, even if you have one right now. Okay, cool. So what do we mean by astronomy from the bottom of the Earth? Well, I'm actually going to be talking about doing astronomy in Antarctica here, and specifically at the South Pole, so the very bottom of the Earth there. And I guess I kind of want to start it off with hearing a little bit from you. So does anyone kind of want to brainstorm with me? Like, we want to do astronomy, and we want to do it in Antarctica. Does anyone have any guesses as to why? Yeah?
Because less interference from cities and
That's one reason. There's another even more important reason. Does anyone want to take a guess at that? Yeah? Oh, that's actually a good one. That isn't on my list, but that's good. So basically, if you wanted to measure the whole sky, you would have to look from like somewhere in the north and somewhere in the south. So that's a good one that's not on my list, but another good one. Yeah? Yeah, that is the big reason. All right, so his answer, if you didn't hear it, was that the air is less thick there. And that's totally true. So the reason we want to do that is that it's very dry there. So that's like another way of saying there's less water in the atmosphere, like the air is less thick. You're at really high altitude, so you don't have a lot of water interfering with your signals. And the photons, which are the particles of light that we're trying to measure with our telescopes, are actually absorbed by water molecules because they're microwaves. And you'll hear a lot about that later, but they're a totally different wavelength from the light that our eyes see. They're kind of the wavelength of light that's actually in your microwave and heats up your food. And the reason your food heats up is it has a lot of water molecules in it, and it absorbs that radiation and heats up. So that's kind of the same thing that's going to happen in the atmosphere with your photons from faraway astrophysics stuff that you're trying to measure. So you want to go to a place that's very dry, really thin atmosphere, and that is a great reason. Yeah, so the South Pole is one of the driest deserts on Earth. And another reason is that it's dark half the year. So you don't have to worry about turning your telescope on and observing during the day, than not observing at night or having interference from stuff at night. So that's kind of just a nice extra thing that isn't absolutely necessary, but it's really nice. And then the other thing is what you said first, is that just there isn't much radio interference from humans. So you don't have a lot of cell phones and Wi-Fi and all of that interfering with the signals that you're trying to measure. So that's kind of a little summary. Why do astronomy at the South Pole? So now I'm going to take you on like a little story of like how we actually get to the South Pole, because I've been there 3 times. A few people in this audience have also been there, so you can probably run into some other people tonight that have been there. And it's actually a really, really exciting experience. So, you know, we all live here in California or somewhere nearby, and how do we get there? So the first thing we do is we fly from LAX on a commercial jet all the way to New Zealand. So that's one of the places that's closest to Antarctica. And when we get to New Zealand, what we do is we actually get something called ECW gear, or extreme cold weather gear. And this is actually a picture that someone took of the wall of this place called the Clothing Distribution Center. And it tells you all the clothes you need. So you need a big red parka made of down. You need pants. You need a jacket. You need this head scarf thing. You need gloves. You need multiple kinds of gloves, apparently. You need goggles, and I don't know what that is. And what's the reason for that? So the highest recorded temperature at the South Pole is 9.9 Fahrenheit. So that's like colder than it ever gets here. And that's the highest temperature at the South Pole. And that was in December 25th, 2011. I think I might have been there then, actually. The lowest recorded temperature is minus 117 Fahrenheit. So that happened in the 80s. That doesn't usually happen, and that definitely doesn't happen while us scientists are there installing the instruments. But it does happen while some of the other scientists are down there running the telescope. So that's kind of intense. And then the annual average temperature is, you know, minus 57 Fahrenheit. And the South Pole is also 10,000 feet above sea level, which is kind of a surprise. Did everyone know that the South Pole is on a mountain? Neither, yeah, you did? But yeah, I mean, I didn't even know that before I went there. But basically, because it looks like a big flat thing, and it really is, but there's basically like a mile of ice there at the South Pole, so it's really, really high altitude. And that's one of the things that actually allows it to have a thin atmosphere that allows us to do our measurements. Yeah. So part of the story for all scientists that go to the South Pole is, yeah, fly to New Zealand, get your extreme cold weather gear, pack it up in a bag, and then fly to McMurdo. Oh, that's what you look like with it on. This is just a random picture of someone all bundled up, but that's what they look like. And this is actually also posted in New Zealand at the place where you leave for Antarctica. So this is what you have to do to even get on the flight to go to the South Pole. You have to have goggles, you have to have the knit hat or balaclava, you have to have your parka on, mittens, wind pants, boots, and apparently you should also bring sunglasses and long underwear. But you actually have to wear this when you get on the plane. So in New Zealand, it's like 70 degrees or something. You have to wear that on the plane in case you turn around, or they said it was in case that you like have to land in the middle of nowhere, which I seriously hope that never happens. But you have to be prepared so that you can get off the plane and be wearing all this stuff. So it's pretty warm. All right, so this is back to our map. We take our path that I've drawn on here to the edge of Antarctica. And we do that on this jet. It's called a C-17. It's a giant jet. It's really big so that you can take a lot of cargo down there, because since you're doing science at the South Pole and also at the edge of Antarctica, there's a lot of biologists and other scientists down there. You kind of use this large plane to fly people and cargo all the way to the edge of Antarctica. This is the jet. It takes about 4 hours. Yeah?
So it's a military jet?
Yeah, it's actually, so they contract with the Air National Guard to fly us. Yeah, the New York Air National Guard. I don't know how that came about, but that's what they do. So it's pilots from the New York Air National Guard that fly us there. It's kind of cool for those who have never been in a military plane. I hadn't, and you get to, you know, like sit on nets on the side, like, I don't know, you feel like you're in a movie. Thought it was pretty cool. People that do that normally probably think it's fun, but I was like, wow, this is awesome. Okay, so step 4. So you get to McMurdo, you're at the edge of Antarctica. That's actually a very beautiful place. And if you're lucky, you get to see penguins and seals. I actually only saw seals from really far away, such that they were like tiny blobs on the ice. And I saw one penguin in all the 3 times I've been there, so it was a little bit of a disappointment, but you know. So then you take a smaller plane to the South Pole, and this is actually the inside of the small plane. So this is kind of us all sitting on the sides, and then this is our bags, and then back there they kind of put some cargo that you need for your instruments. Depending on what flight it is, sometimes this place is all filled up with cargo or telescope pieces, essentially. But sometimes it's filled up with people, like it is here. And that's me. I have a lot of pictures of me in this talk. And this is what it looks like out the window when you're flying across Antarctica from McMurdo to the South Pole. So it's incredibly, incredibly beautiful. All of these mountains buried in snow. It's really great. And then this is what the plane looks like from the outside, and that's right as it's about to land or take off, I can't remember which, at the South Pole with all the telescopes right there. So there's actually a number of telescopes at the South Pole. This is a little bit of an old picture, but this is the South Pole telescope, so this is the one I'll be talking about today. This is the BICEP telescope, and then this is now the Keck telescope. But a bunch of people in Cahill work on these telescopes here, so you can probably run into some people tonight that work on those. But yeah, so that's a plane landing right by all the telescopes at the South Pole. And this is it when it lands. You might notice something special about this plane. It has skis instead of wheels. I mean, it has wheels as well. But it has skis so that it can land on the really soft snow and not get stuck. And then this is what it looks like when people get off the plane. The plane keeps running because it's actually so cold there that you don't want to turn off the plane because then everything kind of freezes up and it's really hard to restart them. So what happens is the plane pulls in, everyone gets off, they unload all the cargo, everyone who's leaving gets back on, and it takes off again. Only if the plane is actually like having mechanical difficulties does it actually stay there. And this is actually, so this is the South Pole Station. This is our home where we actually live when we're at the South Pole. And this is kind of like, I call it sort of a college dorm a little bit. So it's kind of the same way that you would think of a dorm in college, in that you have a cafeteria there, you have like a library, you have your bedrooms, you have a gym, but it's kind of all inside this one building. And that's where we live, and then we work at the telescopes, which are about 1 kilometer away. And there's a lot of stuff at the South Pole because people have to live there. So the scientists like me that are installing the cameras, we actually fly down there in the summer, the Antarctic summer, when it's slightly warmer. And we work there for about 3 months installing the instruments. But then we have a couple of really dedicated science friends that actually stay there the whole winter with the telescope when it's too cold for anyone to fly in and out. And that's when it's dark the whole year and they're observing with the telescope. But there's about 40 people total that stay at the South Pole. And for that reason, they have things like this, so a greenhouse where you can actually eat a little bit of vegetables during the winter that are not frozen. So. And this is the dining hall where you eat, and like it's a very communal atmosphere. And then there's this TV up here, which kind of tells you a bunch of different things on a daily basis. One of the things it tells you is like how much water you're using. So where do you think people get water at the South Pole? Yeah. So it takes a lot of energy, and it's pretty difficult to melt enough water for everyone to drink, let alone shower and all this other stuff. So they keep track of how much water you use. You're really supposed to conserve water, except to drink. You should drink as much as you need. But there's a screen up here that kind of tells you a bunch of stats about the South Pole. And sometimes it tells you the weather. And this is not from when I was there. So this was May 6th, so the dark, dark middle of the winter. And it tells you the temperature and the wind chill. So you can see this is like a very cold day. So that's kind of what you have to deal with. And even in the winter, the scientists that are staying with our telescopes actually walk from that building where everyone lives to the telescopes every day to do work. So anyway. All right, so now we're going to talk a little bit about science. Does anyone have any questions about like the getting to the South Pole first before I go on to science? Okay, cool. You can ask more later. All right, so what kind of science goes on at the South Pole? So one of the things that people do, like I'm not going to talk about all the science because it's a lot, but people study the air and the ozone, because you might know that the ozone hole is right above the South Pole. So the air and ozone are studied. Seismic science is done there. There's one of the quietest places to do seismic observations up near the South Pole. Something called off-world simulations. I actually didn't know what this was, but actually they have some rovers that they want to try on icy planets, on other planets besides our Earth, and they've actually tried them at the South Pole, kind of seeing how they do traversing the land by themselves at the South Pole. So that's something they do there. And then astronomy and astrophysics, which is what I'm going to be talking about today. So one of the main things is the cosmic microwave background. So this is radiation from the Big Bang. I'll talk a lot about that. And then I'll also talk about another experiment that some friends of mine work on that measures neutrinos. So we're going to focus on the cosmic microwave background first. And yes, so what is the cosmic microwave background and how do we measure it? First, I'm going to play a tiny bit of a video just so that you can see. Like this is a video that some people on our telescope made with the American Museum of Natural History. And it just kind of shows you a little bit about what the South Pole is like. I'm going to cut it off before it goes too far because I don't actually have that long to talk. But it lets you see it a little bit.
The South Pole wasn't an obvious place to build a telescope. Winter temperatures go down to about minus 100 Fahrenheit. Add the wind chill and you get about minus 155. The reason we've come here is because it's such a good spot to look at the cosmic microwave background. The cosmic microwave background is often referred to as the leftover light from the Big Bang. It's the earliest light that we can see, light that was given off only a couple 100,000 years after the Big Bang. It's got little hot spots, little cold spots, bumps and wiggles scattered throughout it. And by looking at exactly how those are distributed, we can see sort of a picture of exactly what the universe looked like way, way back then.
All right, so we're going to stop there because we have a lot to cover. But yeah, so basically, as you might have gotten a little bit from this video, there's something called the cosmic microwave background radiation. Raise your hand if you've ever heard of that at all before. OK, so a lot of people have. Awesome. It's good. It's very famous radiation. So anyway, so the cosmic microwave background is the oldest light in the universe, and it came from right after the Big Bang. And this is like just some sort of interesting artist rendition of the Big Bang, and this is supposed to be like early in the universe, and that's later. I don't really know, but it's kind of cool. Right, so now we're going to talk a little bit about what this means. So if you're looking at the cosmic microwave background radiation, it's kind of the earliest light in the universe. So kind of you're seeing something that happened right after the Big Bang. Well, what does that mean? So I'm going to throw out there something which is that looking back in space is kind of like looking back in time. And if that doesn't make sense to you right now, hopefully it will in a second. So does everyone know about the speed of light? So the speed of light is the fastest speed in the universe. Nothing can go faster than the speed of light. But the speed of light is finite. So light takes a certain amount of time to travel from across the room even to me. But it's really fast. But it does take a certain amount of time. So if you look from Earth, so this is us here on Earth, and you look at, say, the sun, not directly at it, because that's not a good idea, but you see light from the sun, it actually takes 8 minutes for that light to travel from the sun to us. And that's 93 million miles. So if it takes 8 minutes from the light to get from the sun to us, then we're seeing the sun as it was 8 minutes ago. Does that kind of make sense? All right. So if we now get a telescope and we actually look at the nearest star to us, that light that's coming from that star takes actually 4.4 years to get from that star to us. And that's 20 million miles away. Like now we're getting into number quantities that don't even make sense to me, but just million. All right. So if it takes light 4 years to travel from that star to Earth, we're actually seeing that star as it was 4 years ago. So we're kind of now in this time machine where we get to see things that are close up as they are now, but things that are far away, we're seeing as they were pretty far back in time. So now if we think about looking at the nearest galaxy, so some people, you might have heard of the Andromeda galaxy. It's a beautiful spiral galaxy, and it's the closest one to us. So that actually takes the light 2.5 million years to get from that galaxy to us. So it's 8 billion miles away. And now we're seeing Andromeda as it was 2.5 million years ago. So now if we think about looking at that cosmic microwave background radiation, so we're actually looking at something that was emitted about 13 billion years ago, because the universe is 13.7-ish billion years old, and that cosmic microwave background radiation was emitted right after the Big Bang. So it's 4,000 billion miles away-ish. There's other factors in there, but we're basically looking at something that was emitted 13 billion years ago. And we're seeing the cosmic microwave background and really the universe as it was 13 billion years ago. So that's kind of really exciting. And what we do with our telescope, this amazed me. I built an instrument and took it to the South Pole, and we turned it on, and we measured that light, and we made a map that looks something like this, and it's just, doesn't that blow your mind? You're like, this is something that actually was emitted 13 billion years ago. It's impossible to comprehend, but still awesome at the same time. So that's what we're doing with these instruments, is we're measuring the history of the universe, like really the very, very beginning of the universe. And this is just kind of a bigger picture. So this is actually a map that wasn't taken with the telescope I'm talking about today, but something called the Planck satellite. So it's a similar instrument, but it was in space, so they could actually measure the whole sky. So they measure the whole sky kind of like this, and then we measure kind of a smaller patch of the sky, but really, really sensitive. So we're kind of complementary instruments in that way. So this is just a little cartoon of this telescope while we're looking at the cosmic microwave background. And we'll skip that because we're kind of out of time. But and then I've mentioned this a few times. So this is a little drawing of the electromagnetic spectrum. So we have radiation from gamma rays, which are very, very high energy, all the way to radio, which is kind of something you actually pick up with your radio. And in the middle, we have visible light that our eyes can see. So this is just kind of showing you the wavelength of that light, how its wave is. is much, much tinier over here for these really high energy radiation, and then over here it's much bigger for this microwave radiation. And that is just why I've been calling them microwaves, because they're kind of in this wavelength range. And then that kind of goes back to the question that I brought up before, which is just why are we at the South Pole? And that's because we're trying to measure those microwaves, and they get absorbed by water vapor. So now I'm just going to show you a few pictures of the South Pole Telescope and what the camera looks like, so you can kind of get an idea for what it really is. So this is the South Pole Telescope. It's a 10-meter dish. You can't see all of it because the shield is there. But this is the dish, and then this is where all the instruments, like the camera part, goes. And this is really similar to something like this. I don't even mean to advertise for them, because I don't know. I've never even had that TV. But it's very, very similar in the way it works, in that, you know, stuff bounces off and is absorbed in some sort of receiver here. This is the receiver there. And this is just another picture from the front. So this is actually 10 meters there, so it's a really, really tall telescope. I've actually stood up there. It's really cool. And then this is the inside of the telescope. So it just looks like a big jumble of wires, which it basically is. This is the equivalent of this camera. So if you're looking to take a visible light picture, you can use a camera like this, or now on our phones, whatever we have now. This is the equivalent for microwave radiation, is this with all of this electronics in there. And we're going to skip that because we don't have that much time. But basically the way things work is that you have the cosmic microwave background radiation. You know, it's emitted. It hits this telescope. It gets focused onto the detectors here. And these are the super sensitive detectors that we build here. And then that goes to kind of a circuit board, which goes into your computer. And then you read out and make a map of the cosmic microwave background. And that's really how it works. It's kind of incredible. So now I just have some more pictures of the actual insides of the telescope. So this is me working on the inside of the camera. And this is some colleagues of mine actually working on the lenses. So you know how your camera has lenses that actually focus the light there? So do the cameras that we use for the cosmic microwave background radiation. So do you notice anything weird about this lens? Yeah, I heard someone say it's white. You can't see through it. So it's actually opaque to visible light. So the high energy light that we measure with our camera and that our eyes see actually can't get through that, because that would actually heat up our detectors. But the really low energy microwave radiation that's this longer wavelength actually just goes right through there. And you can actually kind of measure that radiation there. So that's a lens just in the same way. These are all like analogs of that. So we take this big camera that's a jumble of wires. We put it together at the South Pole. Then we attach it to this big other thing. Oh yeah, the other thing I forgot to tell you is that all of this is under vacuum. So all of this is in a vacuum, because if you actually let it be in the normal air like we are in right now, that air would actually heat up all of the detectors and you wouldn't be able to measure your signal. So all of that's in vacuum, and all of it's cooled down to super, super cold temperatures. And then we put that in this receiver cabin, and then there we measure it. We measure the cosmic microwave background with the South Pole Telescope. So yeah, that's that. I think we have a tiny bit more time. Oh yeah, so this is a picture of us the first time our telescope worked. So that's just like the happy faces of scientists when you're like, ah, that's me. And there's like people taking pictures with their camera of my screen, which had like our first light. You call it first light because it's the first time we observe something in the sky. So that's just the happy faces of scientists making their instrument work. And then that is just a beautiful, beautiful picture of the South Pole Telescope. And oh yeah, I want to tell you one more thing before we finish. I can see you over there. So what do we learn from looking at the CMB? So I kind of mentioned that a little bit before. We're learning about the universe as it was. So that's a picture of me. That's my baby picture. So basically what the CMB is a baby picture of the universe. So it's the universe when it was really, really simple. Now we look out in the universe and there's stars and galaxies and gas, and it's very, very difficult to understand. Astronomers here at Caltech and all over are doing that, trying to understand the universe. But what we want to get is kind of a basic idea of what it was like to start with, when it was really uncomplicated, when it was just like happy-ish Abby at the very beginning. So this is kind of our baby picture and the thing that kind of gives us the initial conditions to like figure out the rest of physics and astronomy today. So yeah, that's it. Yeah. So oh yeah, we learned about the CMB. We learned from the CMB the shape of our universe, dark energy, dark matter, all those things that you can ask the panelists that come up here after. So yeah, that's it.
Thanks, Abby. We have about 5 minutes to ask Abby whatever questions you might have. If we don't get to your question, don't worry. Afterwards, you'll have the opportunity to come up and chat with her more.
How long did it take to make the telescope?
Great question. So the telescope itself, that was built in basically 2006, and they actually assembled just the telescope parts itself in 3 months, because that's like the longest amount of time you have at the South Pole when it's still light outside and everyone's there. So they actually test assembled it. It took about 3 months in Texas, and then they reassembled it at the South Pole. And then the receivers themselves actually take longer. They're even more complicated because you have to make all of the individual detectors. So how our digital cameras are essentially like off the shelf. They make many of them. But these cameras are very specialized, so they're made by only a few universities in the world. That actually takes about 3 years. So it takes 3 years to kind of get from the beginning of the design to the end. Yeah, there's a question.
How much did the telescope
Yeah, great question. So the South Pole Telescope is funded by something called the National Science Foundation, and they do a lot of basic science research funding, and it costs about $15 million for the whole thing. The cameras themselves cost a couple $1 million. Yeah. Is there a question up here? Yeah, so it actually doesn't, so it actually is pretty dense at that time when the cosmic microwave background was emitted. It was basically when the universe had started to cool off, and it was it was basically just cool enough that radiation could get out. There were a lot of particles that were really close together, and sometimes the photons will try to kind of go, but they'll run into other things. When the first light was emitted was actually when that universe expanded and was not as dense anymore, and the photons could actually travel and just start filling up the universe like they are now. So it's pretty dense, but not the most dense it ever was. It was the least dense, actually. All right. Yeah, there's a question back there.
does every star in the universe in space have
Yeah, that's a good question, almost philosophical. So, yeah. So the interesting thing is, when we look out into the universe, we basically see the cosmic microwave background and stars and galaxies in every direction, and it kind of feels like we're the center of the universe, but we're actually not. So if you are on another planet, on another star, and you're looking out at the cosmic microwave background, you would actually see not the exact same cosmic microwave background, but you'd see the same sort of patterns in the sky. So you're all seeing the same cosmic microwave background, but you're at a slightly different position, so it's a little bit different. But yeah, it's a good question. Yeah. Yeah.
Abby, I think you ought to tell them that on July 1st, it was the coldest and darkest. It gets to be 100 below. The people who were down there take off all their clothes and they run around the South Pole.
I don't know. I've never been there at that time. I only go there in the summer when it's light outside all the time.
What they do is they go to, they get to 200 degrees hot bath, and they soak in that first. Then they run out and run around.
All right. So actually, it's actually really awesome to be there in the summer because it's light all the time. So actually, you know how you kind of have your body kind of responds to when it's dark outside? You're kind of oh, I just want to stop working and go to sleep now. It's light outside all the time in the summer, so you can actually work way longer hours. So it's kind of like playing tricks on your circadian rhythms or whatever they are. All right. Any other questions?
I think we have time for 1 or 2 more questions, so.
Now's your chance. Yeah, someone in the back. Yeah, that's a really good question. So one of the hardest things to distinguish between the cosmic microwave background and other microwaves is that our atmosphere also emits in microwaves. So it's our biggest source of noise. So what you actually do is that you take your telescope and you kind of point in the same place on the sky, and you go back and forth over and over again. And you go back and forth over that same patch of sky hundreds and hundreds of times, basically every day. And the other microwaves will fluctuate, and they'll kind of be noise. And they'll actually sometimes be bright, but sometimes be dim, because they'll just be the atmosphere moving around. And then the cosmic microwave background always has the same pattern. So it'll actually kind of start to, you'll sort of start to integrate down and get a better signal in the cosmic microwave background and kind of a worse signal in the noise in some way. And then there's other stuff. So there's other things like, say, like other galaxies that are bright in microwaves also. The thing about those is that they're very localized, so they're like points. So what we do when we make that map of the cosmic microwave background, you actually see like all that kind of light and dark spots, but then we actually have a few bright spots that are actually things that we just mask out when we make the measurement of the universe. So we just basically do it based on what they look like spatially. And then let's see what else. Oh yeah, there's also our own galaxy, which emits microwaves as well. And in all the pictures of, so all of these pictures, before they subtracted out the galaxy, there's like a big like bright thing right here, which is like our galaxy in microwaves. So actually, when you're measuring it, you really only get like some clean spots like up here. So it's actually a lot more complicated than it looks. Yeah. Yeah.
So I think then your work brings more granularity to the overall picture rather than array local space.
Yeah. So what ours does is that it has. So there's a difference. So if you have a really big telescope, you can see tinier things. So that's one thing that our telescope does that others don't, is that we can see really small scale things.
So where would be your reading?
So they would be like a square like this, kind of like a smallish square. And then if you zoomed in, like you could see this at much higher resolution. So you could see smaller scale fluctuations. And then you would kind of see them with better contrast in some way. Yeah.
Okay, I think I'm going to have to cut it off there. So let's thank Abby again. Okay, let's get started with our Q&A. This is pretty informal, so like I mentioned before, if at any point you want to head out and check out the telescopes, you're welcome to do that, and then if you want to come back in, you're welcome to do that as well. To start, I'll just ask our 4 panelists to go down and quickly introduce themselves, and then we can get started, and you could ask whatever is on your mind. We have some suggestions up here based on what their areas of expertise are, but if you want to challenge them by asking them something totally unrelated, feel free to do that as well.
Hi, my name is Drew. I'm a postdoctoral researcher here, and you can ask me about black holes and stars and what happens when these two things meet in the universe.
Okay. Oh yes, like a hello. Oh yeah, like my name is Tim. I'm a grad student from Canada actually, and I'm just here visiting, and I do a lot of work on galaxies. So yeah, feel free to ask me like anything galaxy related.
Hi there, I'm Matt. I'm a graduate student here. I study how star formation happens in galaxies and how planet formation happens around those stars. I also know a lot about space travel, so that's on my side too.
Hi, I'm Denise. I'm also a grad student here, and I do a lot of work both on galaxies and on the early universe and cosmology in general. So feel free to ask me any questions about dark matter or any crazy questions that you have about the universe. I'd be happy to answer them.
Microphone for the audience.
Oh, that's a great question.
So no pun intended, but what light has CMB shed on the dark matter and dark energy? How do we connect it to us?
Okay, I can take that one. So there's a whole lot of things that we can learn from the CMB. And one of our best techniques for studying the CMB is a mathematical technique called a power spectrum. And that's just a fancy word for studying these fluctuations in the CMB, these ripples, and what they can tell us about the universe. And so one of the things that we can learn is from these ripples, we can see that there were sound waves in the early universe. And we can measure approximately how much matter there had to be to produce those sound waves. But dark matter can't produce any sound waves because the particles don't interact with the electromagnetic force. That's why it's dark, because light is electromagnetic. And that's the force that allows particles to interact with each other. So since dark matter particles don't interact with each other, they don't produce these sound waves. And so we see a mismatch between the amount of matter that the CMB tells us we should have and the amount of matter that we actually observe in the universe. And so that's one of the clues that tells us that there has to be dark matter.
So we don't seem to have an extra microphone, so I'm just going to ask that the panelists, when you receive a question, if you could just repeat the question back.
Oh, sure.
If you have it recorded, that would be great.
Will do, will do.
And dark energy as it relates to CMB?
Yeah, dark energy relates to the CMB. So this is a little bit more technical, but something else that we can learn from the CMB is to do with the expansion history of the universe and the sort of shape of the universe as a whole, its geometry. And so dark energy influences the geometry of the universe, and it influences the rate of expansion of the universe as well. And we can see signatures of that in the CMB in addition.
Why do you listen to the talk of the chapter? Why microwaves as opposed to anything else that gets shot out of anything else?
Okay, so yeah. Oh, yes, we observe the microwaves because that's just, yeah, the wavelength like that the CMB happens to be at. So like it wasn't actually like emitted, like a microwaves, but because like the universe is expanding, like the the wavelength of the photons like expands. So so like now like it's in like the microwave band. So like if we were to try and observe it, let's say 10 billion years ago, like we would have to go to like a different wavelength. But it's just like that. That's the wavelength band like that the CMB like is in right now.
And also, moreover, since the CMB is very cold in the sense that it looks like thermal spectrum, the heat at which, like if it were an object, like a fire poker you have in the fireplace glows red because it's rather hot, the CMB is incredibly cold. It's about 2.73 Kelvin. And so because it's so cold, the peak, where it emits most strongly, is in the microwaves. Well, yeah, for us, it's in the microwaves. Yeah.
You were talking about the sound imprinting on the CMB, and a couple of months ago you guys had a lecture on the presentation about the gravitational waves. So the gravitational waves also getting stretched as the as the universe is expanding. Do you see any imprinting of the gravitational waves on CMB or the other way around, and how do we combine these two concepts together?
So yeah, there is some. Oh, right. Yeah, the question was, is there any evidence for gravitational waves in the CMB? And the answer is, right now, we don't see any strong evidence for gravitational waves in the CMB. But there should be some evidence in there because the CMB is basically created by these huge amounts of matter that are moving around at very high speeds. And that's exactly what you need to create a gravitational wave. A couple years ago, a group who was using that BICEP telescope that's down at the South Pole thought they could detect the signature of these gravitational waves from the earlier universe in the fluctuations in the CMB. But it turns out it was actually just some dust in our own galaxy that was kind of masquerading as these gravitational waves. And so right now it's not so clear that these have been detected, but they should be there. It's just a very difficult measurement to make because it's such a small signal on top of the rest of the stuff that's in this very smooth CMB.
Understand exactly how they measure the gravitational waves. I know it's a interferometer, so you can measure the differences in path length because the gravity wave goes through, it will maybe stretch space a little bit. But to me, so far, the numbers don't seem to add up. I think the wavelength of the laser was like 1,000 nanometers. No, yeah, maybe 10 or something like that. In the infrared. But the string was stretched like 1 part in 10 to the 21, or something like that. So, what fraction of a path length difference was actually measured because it's such a small amount of a wavelength of the laser light?
Yeah, I'm not an expert on LIGO. You've basically just said everything that I know about LIGO, so I can't help you with that question. But yeah.
My understanding is that, again, as the arms are stretched and squeezed by the passing gravitational wave, some small amount of light leaks through, and I think the difference between it being the two wavelengths being perfectly aligned as it comes back, and when like the peak of the gravitational waves are coming through, I think it's thousandths or tens of thousandths of fractional wavelength. So it's a very difficult measurement, and a ton of what they do is work on just understanding the noise in their own detectors. Some of my friends who work on the noise calibration are worried about things such as interns walking around and stamping around the control room and logging operations happening 20 miles away from the trees hitting the ground and making the earth ring. So it's incredibly difficult. Most of their work is dealing with the noise. The distance that the CMB is from us in all directions, or other things that we're observing? So the CMB is effectively the furthest away thing that we can see, the oldest thing we can see, because before that's sort of, that's not the dark ages, but it's, the universe is opaque. And so things that are closer to us take less time to reach us naturally, since the CMB is the furthest thing that is from us, the furthest away thing from us, and the galaxies and stars and all the intervening material, it takes less time to reach us. So as you get closer to us, things take less time to reach us. So we see things less far back in time as you march towards us.
I want to follow up on that same concept. How are we measuring, how are the waves coming back at us? Everything's expanding, and yet you're measuring something that's farther away from us than, like, is it a reflection off of that? Is it radiating from the periphery back in?
Okay, so I think. Could you repeat the question? Yeah, so I guess your question is sort of how are we able to see the CMB, at some distance from us if it takes some amount of time to get to us. So I think this might be easier if I draw a little diagram. So I'll draw us right here. Ooh, this is sort of wobbly. Okay, and so say we're looking at, stars within our own Milky Way. We see these stars, and the light reaches us, and it's all great. And then if we look even farther away, we can see some other galaxies, and that light travels to us, and we see it. And, that light takes longer to get to us, so maybe stars within the Milky Way take, a few hundred years to get to us. Light from another galaxy maybe takes a few 100 million years to get to us, or even more. And then if we look even farther out, we can see the CMB. And the reason that we have to look so far out is because the CMB was created so long ago, about 13 billion years ago, that it takes a long time for that light to reach us. And so if we want to see light that left the CMB 13 billion years ago, we have to look 13 billion light years away. So the CMB actually exists everywhere in the universe, but the part of it that we're seeing is the part of it that's at the correct distance for that light to take that exact amount of time to reach us. Does that make sense?
I guess my confusion is that is expanding, correct? Sorry.
Mm-hmm.
So that light is traveling faster than expansion? I don't know.
So it's not entirely correct to say that the light is traveling faster than the expansion, because it's space itself that's expanding and the light travels through space, if that makes sense. So yeah, you can.
Also, as the horizon is moving away from us, so as the universe is expanding, the light is being stretched out by the expansion of space. So the CMB is getting colder all the time to us because the light is losing energy as it's getting stretched away. So though the universe is expanding and the horizon is moving away from us, we're still able to see it because it's not going faster than the speed of light for us. And so the light that we see from it just gets fainter and fainter and colder and colder. And so that surface that we see is where in the universe we can see to, which is the first time light was able to actually escape out of this primordial soup. And so that just, for us, again, happens to be 13.7 billion light years away. Okay, it's like 300,000 years after the Big Bang it happened. So 13.4 billion light years away. Yes. Does that help?
So then, like, if you measure that from, let's say, right now we're on the Milky Way, and we measured it, it would seem shorter, or right, than from the Earth. So then it just depends on where you're measuring it from.
So wherever you are in the universe, you would still see the cosmic microwave background being the same distance away. You're just seeing a different horizon, since the light from wherever you are in the universe takes 13.4 billion years to get to you. And so the horizon would sort of look statistically the same. It would have bumps and wiggles all over, but it wouldn't be the exact same bumps and wiggles that we're seeing, because we're seeing light coming from a surface that's far away from us. So again, I guess, yeah, Denise.
Yeah, so suppose we have some aliens who live over here. They're going to see the CMB still 13 billion light years away, but they're seeing a different portion of it. They're seeing this surface right here. But they're still able to see it because the CMB exists everywhere in the universe.
Because it exists everywhere in the universe, because the CMB is originating from a point in time where the whole universe finally was thin enough that light could escape through it. So at that point in time, like, the universe gets thin enough that light just starts running off in all directions. And we see the CMB as that light that finally reached us from incredibly far away. And so if you were somewhere else in the universe and you looked for light that was coming from 13.4 billion years ago, you would see these bumps and wiggles and a cosmic microwave background. But it would be slightly different.
So if you kind of rewound the tape and went back 13.5 billion years ago, the CMB would then become shorter and shorter and become more high.
Yeah, you would not be able to see as far out into the universe.
And what would be the limit?
Well, when you're in the soup.
Well, the CMB was originally a bunch of gamma rays that were created as pairs of particles annihilated with their antiparticle. And that's basically what was going on in the early universe. You had all these particles and antiparticles annihilating and creating these high-energy gamma ray photons, which were basically trapped in this dense particle soup. But finally, when the universe was about 300,000 years old, the density was low enough, and the temperature was actually low enough that electrons could join with nuclei and create atoms, and that's what made the universe transparent to this radiation. And it's been traveling to us ever since then. But because the universe is expanding, those photons are losing their energy. So they've gone from gamma rays to X-rays to ultraviolet to visible to radio. Now they're basically microwave or radio waves.
So CMB is no different from the redshift that we were talking about earlier. The basic idea is the same, it's just at a different scale.
Right. So the CMB is the most redshifted thing we can see, because it's the first time light was able to travel through the universe. And so it was originally very high energy gamma rays, but after traveling in this expanding universe for so long, it's been shifted all the way down to the microwave.
It's a good way to think of, why is it that we see some cosmic background and the alien sees something different? Maybe a good way to imagine how that could be is, let's say our universe is actually just a sphere of, or the surface of a sphere, like the moon. And so we're on one part of the moon, aliens on the other part of the moon. And then the moon, with the Big Bang, or the expansion just inflates and it's bigger and bigger and bigger. It's going really, really fast. And so now the universe is very big, the moon is very big, and so we can only see this far out onto the moon, so we cover like half of the balloon. The alien covers the other part of the balloon. So there's I guess a lot of the universe that we actually can't even see.
Right. There's a difference between the universe, which is supposed in our theories we call it this infinite thing, and then there's the observable universe, which is for any point in the universe you can only see you can only see in this sphere that has a radius of 13.7 gigalight years.
Does it part, do we know how big the whole thing is compared to the visible parts?
Well, when we think about it as infinite, and we're just seeing some sphere of radius 13 gigalight years. amongst this infinite expanding universe.
Oh yeah, so we don't actually know how big like the universe is. Oh yeah, we know how big it is. Oh yeah, like at earlier times. Oh yeah, like compared to like the size today, but like we don't actually know like the complete size of the universe.
And one of the other kind of interesting things we can learn from the CMB along these lines is that, you know, Abby showed us this map of the CMB, and it had all these fluctuations, all this structure to it. But those fluctuations are only, you know, 1 part in 100,000. The temperature of the CMB is actually remarkably constant. It's almost all this 2.73 degrees Kelvin. It's just these very, very tiny fluctuations. And so the only way to explain this remarkable degree of uniformity is to have had all of those different pieces of the universe. They had to be in causal contact with each other. They had to be able to communicate with each other to say, you know, we're going to be this temperature now. But we know from measuring these distances on the sky, there's no way that light could have traveled from in all these different regions. So it tells us that there must have been some time in the very early history of the universe where the size of the universe increased at a tremendous rate, and we call this inflation. And it's another one of these periods where something similar to dark energy causes the universe to expand at quite an alarming rate. And that's the only way we can explain this remarkable uniformity of the CMB.
So in terms of the spectrum of the CMB, what do you have next? You said that it's opaque after that, but could there be some form of energy which we haven't discovered yet? Take us farther back in time than 50 years?
Well, I mean, the thing that you can't see anything that emits with electromagnetic radiation beyond the CMB, but you can detect gravitational radiation from earlier in the universe. And so what people have been looking for, as I was saying earlier, is that, you know, there should be some imprint of the gravitational radiation that was created in the early universe that you can detect in the pattern on the CMB. And, you know, there's no limit to how far back we can see these gravitational waves. This limit of, you know, this 300,000 years after the Big Bang is only for electromagnetic radiation, but we should be able to see gravitational waves all the way back to the Big Bang itself. We don't know how to do that yet. It's a very difficult measurement to make, but theoretically it can be done.
Can I interrupt? Sorry. Can I get you to speak into this thing? And then I'll pass this one around. Thanks.
So just to follow up on that then, so theoretically one could conceive of some form of energy, may not be electromagnetic, may not be gravitational, something else, where we could look beyond the Big Bang as well, or is that like a complete dead end where it's a singularity and you cannot just, can you categorically say that beyond that you cannot see at all, or it's possible that something might happen 1,000 years from now?
Okay, yeah. Well, like the thing is that we don't really know what happened before the Big Bang. Like it's sort of beyond the realm of measurements, I would say, is like a good way of putting it. So like there's, yeah, oh yeah. Like I don't think there's any way we can possibly measure it just because it's like, I don't know, it's like not, okay, here.
It's a categorically difficult question.
Well, and to add to that, it's not even clear whether before the Big Bang is something that exists at all. You know, it's possible that the Big Bang was sort of just the beginning of time, and that it doesn't even make sense to ask what was before that, if that makes sense. So it's sort of a vague, it's sort of a philosophical question almost to ask.
Unless you get into the multiverse kind of theory and you've got lots of these Big Bangs going on everywhere.
Yeah, well, yeah, we can let Sean Carroll talk about that one.
I have a question. I'd be curious to know how each of you got particularly interested in your respective topics.
Okay. I don't know. I guess I was always sort of interested in galaxies. I think I'm very interested in physics and in mathematical techniques in physics, and I think that there's a lot of interesting physical processes that go on in galaxies, and I think that the study of cosmology in particular is an interesting opportunity to apply a lot of math. So I guess that's how I got interested in my field of study.
So I grew up in La Cañada, and a lot of my friends' parents worked at JPL, so we got tricked into going on to lots of field trips to JPL, which was really neat. And I went to undergrad to build rockets, and I thought space was really cool, so I started to study space. And that's how I'm sitting in this chair now. They also tricked me into sitting here.
Oh, yeah, so I'm pretty similar, to Denise, where, like, I was never, like, that into space. Like, I always thought it was cool, but, like, I was more, like, interested, like, in figuring out, just, like, in physics in general. So just, like, figuring out, why things, could work the way they do. And then it turns out there's, like, a bunch of outstanding questions in space, like, we don't really know, like, what's going on. So it's just, like, a neat way, like, of, exploring, unknown ideas.
Yeah, I guess like everybody up here, I took a really weird path to get here. I went to college to study film. I went to film school, and I had to take an astronomy class as a gen ed thing, and I thought it was pretty cool, so I stuck with it. As far as my particular interests in black holes and interactions between black holes and stars, that's also kind of a random thing. When I went to graduate school, I really wanted to study particle astrophysics and work on this neutrino detector that Abby talked about a little bit down at the South Pole. But then the first summer after I was in grad school, a professor friend of mine said, why don't you just try this one project where you simulate what will happen if a dead star gets too close to a black hole. And I had a lot of fun doing it, and I kind of never looked back. So.
Okay, another question. Is it on? Yeah. So, well, maybe the easy way to ask the question is, I asked something like this before, but nobody knew, so maybe you guys know. How come there's just as many electrons as protons around here? So it seems like there's a perfect balance of charge now, but where did they come from? Well, I guess one mystery is we don't know why there's more matter than antimatter, maybe, or maybe the explanations are complete there. But beyond that, I guess quarks kind of froze out after like 3 seconds or 5 seconds, depending on who you talk to, or something like that. And then it took a lot longer for the universe to cool enough that electrons froze out. But why would we have just as many quarks as we have electrons? That's the question.
I didn't know last time, I still don't.
I know.
Okay, so the reactions that created these quarks and electrons are necessarily like a conserved charge. So the fact that there's as much positive charge as there is negative charge maybe isn't that surprising when you think about the fact that all the reactions that created them had to conserve charge.
But like a photon, well, you can create particle-antiparticle pairs. I think that's how when there's enough energy to be creating these particle-antiparticle pairs, you have a whole bunch of them, and then when it cools down enough, then somehow, well, I guess the baryon symmetry says 1 out of every billion of those particle-antiparticle pair reactions gives you an extra particle instead of an antiparticle. And that's why we have more quarks instead of antiquarks. That's why we have more electrons than positrons. So, but I thought that the main reason or the main creator of electrons was this pair antiparticle production that then froze out and you got extra electrons. But then why do you get more extra electrons than you get more extra quarks?
I think the real answer is that nobody actually knows. But again, my best understanding is that it's really sort of a kludge that we say, okay, well, you need 1 out of a billion, extra extra electrons versus anti-electrons, and that way everything sort of, annihilates, makes enough photons, and the charge works out. As to why the universe isn't charged, that's another question that I frankly think nobody actually knows the answer to. But it's a great question, and there's a lot of people over in Loritz in the building across the street who are worrying about that, and we should get some of them down here, because I think you need an astroparticle physicist to tell you why more than...
Or maybe there's extra electrons or extra quarks, but, you know, since the electromagnetic force is so much stronger than gravity these days, it would just, if there was an extra amount somewhere, they would just quickly dissipate, and so you maybe don't notice that they're around. I don't know.
And charge does have a tendency to screen itself, like you explained. But again, as far as we can tell, the universe isn't charged at all. Because even if there was a little bit of extra charge, we might be able to see the fact that there's a little bit extra charge. But again, as far as we can tell, even with the screening, there's still, it's a chargeless universe as far as we can tell.
I see.
What other questions do you all have? Okay.
Yeah, we're talking about, you know, the aliens see something that we don't see. We know how big the visible universe is. We don't know how big the whole universe is. Maybe it's infinite, maybe not. But doesn't the part that we don't see still affect our part somehow? I mean, for sure it doesn't affect where we are, because even light or anything that travels at the speed of light doesn't. But, you know, halfway between where we are and where the alien is, you know, they see a different part of visible universe, and so it seems like the part that we can't see affects the whole of the part that we can see.
Again, so the question being, can't the parts that we can't see affect the parts that we do see? And the answer is they do. We just haven't seen what they've done to that part of the sky yet. Because again, the furthest away anything could cause something to happen where we are is the CMB, because that's, you know, photons have been running away for as long and as fast as they can from that horizon. And anything that was behind that horizon, that light or, you know, doomsday device from whatever Marvel universe you want to pick, that hasn't reached somewhere that can affect us yet. So sure, maybe it's, what, 2.5 million years away is how far Andromeda? So say maybe 2 million years ago, Andromeda just exploded for some reason because, again, some supervillain did something there. We still wouldn't see it for another 500,000 years. And it's the same thing, that this could have come from a supervillain there, or just the fact that our universe is colliding with another one in some crazy multiverse foam. But we just haven't seen the effects yet. So sure, stuff's happening all the time, but it takes a while for the message to get to us.
I have a question for those of you who study galaxies. Can you talk a bit about what's weird about our own galaxy, the Milky Way?
So I learned something cool a couple weeks ago that I actually didn't know before. Is there an eraser I can erase?
Your hand?
I'm not, yeah. This is a nice shirt, man. Okay, so we always think about our galaxy as being like a nice disk, right? Oh yeah, like this is like the typical, oh yeah, this is the typical view of the galaxy. This is a couple 100 million, like a million light years across, and we're, and we're right about here. Oh yeah, but like actually because of like the Andromeda galaxy, which Matt was talking about as being like the closest other galaxy, the disk of our galaxy is actually tilted about, maybe not that much, but about 20 degrees. So it's actually not like a, so it's actually not like a, like a nice flat disk like this, which, I don't know. Like I just learned that a couple weeks ago, and I thought that was pretty cool. Yeah. And then away. Yes, like Andromeda's like over here. Right? It's on both ends. Yeah. So yeah, I thought that was pretty cool.
And Andromeda also works.
Can each of you share what would be one of your favorite films that gets the science right, where the physics is right, that you'd recommend that we watch?
Science right. Is the science right? Well, okay, yeah.
Well, one recent movie that we know gets the science right because one of the professors in our building here helped make it and make sure that the science is right is this movie called Interstellar, where a lot of the plot points are based on the kind of crazy things that happen when you get in the really strong gravitational fields that are produced near a black hole. So, time will slow down and you can get very strong waves on a planet, and all of the physics in that movie is done right, done by somebody who helped invent that field, Kip Thorne here at Caltech. So that's one that gets the physics right. It's not my favorite movie, but the science is good. Oh, and also all of the special effects they're not just artistic renditions. They're true, physical simulations of how light bends around black holes. They wrote academic papers about how they created the special effects for that movie. It's like a piece of science in culture.
Besides the sandstorm at the beginning, The Martian's fairly faithful to science. I also really liked October Sky, but I saw it when I was younger, so I can't say just exactly how scientifically accurate it is, but I think they did a pretty good job. Anyone know?
It was pretty accurate. I mean, it wasn't really like science fiction, October Sky. It was more of a based on a true story kind of thing.
So it was cool.
Movies? Yeah. No, yeah, I'm sorry, I can't think of any others. Oh, yeah, the Interstellar one. The Interstellar one really does. You get a good job with the science.
Aren't you guys missing Contact?
Much as I'm a fan of Jodie Foster, I don't think that movie's really that scientifically accurate, but it's still a good movie, and I do enjoy it.
And some real cool cinematography in that movie too. This is more just off the cuff, but there's this one scene in Contact where Jodie Foster's running through the house because her dad just had a heart attack, and it was really cool because they shot the entire scene backwards, where they were taking the camera was looking into a mirror that Jodie Foster was running at the whole time. Then eventually the mirror stopped, and then she grabs the mirror and opens it, and it's like the camera's just looking at her, and it's like a really cool single camera shot for a minute or something. But this has nothing to do with the scientific accuracy of that, other than just a really cool shot from a movie.
Oh, no, yeah, I can't really think of any others they get the science really right. Well, I'm sure I could, but it's not off the top of my head right now. I'm sorry.
I can think of one particular scientific thing that was sort of correct in something that was otherwise not very correct at all. So in Star Trek Voyager, they take quite a lot of liberties with the science, but one thing that they did get right is that if you end up on the other side of the galaxy, it's going to take you a very, very long time to get home. So the plot of that show is that their spaceship somehow ends up on the other side of the galaxy, and then they're trying to travel home. And of course, they have warp drive, so it doesn't take them as long as it should in real life, but it's still, the premise is something that's sort of based on sound scientific principles. That's about the most that I can say about the scientific accuracy of Star Trek, though.
Apollo 13, there's a movie. It was also sweet because all of the zero-G shots were shot in zero-G. They did it on the Vomit Comet that NASA has, or had. I guess the program sort of shuttered. And it's also why all the shots are only 30 seconds long when they're in zero-G, because that's the length of time through the arc. And so in a bunch of the scenes, you can tell at the end of the shot, a bunch of stuff starts drifting across the screen because they're starting to pull out, and Tom Hanks is just going to hit the wall or something. But sweet movie. Go watch it again. It's also 20 years old or something. I'm an old person now.
Have you read about this trip to Alpha Centauri? You advertise yourself as somebody who knows something about space travel.
Yes.
What do you think of it?
I think it's awesome because we're finally going to build a Bond superweapon, or a Bond villain superweapon, because the idea, for those of you who haven't heard about it, is that we would send sort of a mothership out into sort of Earth orbit that would spit out picnic table-sized iPhone things that we would then shoot a massive laser at, and then that laser would just knock the thing across the solar system towards Alpha Centauri, or Proxima Centauri, the closest star. And the idea would be that we would take pictures or have sensors on board and, you know, get some data from over there, and we would shoot a lot of these because we have no idea what would happen if we send something at an appreciable fraction of the speed of light through the interstellar medium, because if it hits a dust grain or a micrometeoroid or something, it might just destroy it. So we'll shoot a bunch of them, and maybe a couple might make it. And the idea is that in the Atacama Desert, we would have basically a laser superweapon that would charge up from like 10 square miles, or no, 100 square miles of solar panels for one laser shot a day at this thing. And there's a lot of politics that might go into building such a thing, because people say, oh, well, wouldn't it be better if we could put it on Mercury, where we could, you know, be much closer to the sun and get a lot more energy, and we could do it quicker. And the comeback for that is you don't usually like putting laser superweapons where you can point them at anything. So if you put them up in the desert and you can only point out from the Earth, people might like that more. But it could be super cool. Yeah. And it would take 20 years to get our iPhone superweapon camera thing to Alpha Centauri. So that's pretty nifty. It's a human lifetime.
Oh, I just thought of two other kind of news items. Maybe you guys know more about it. I heard they found a 17 billion solar mass black hole somewhere where they didn't expect to see it because it was very isolated, not a big cluster of galaxies. And I think this was like last week. That's one of them. And then the other one that I saw was they also found a whole bunch of galaxies that have black holes in the middle, and their jets that they eject are all aligned in the same direction. I don't know if you guys know any more about those stories.
I read about the alignment one, and my conclusion isn't that nifty, but I think that it was statistically unlikely that they found it this way, but not necessarily something that's impossible. That if you're looking at, you know, tens or hundreds of thousands, I think, what is the Sloan Digital Sky? How many galaxies are in that?
Millions.
Millions. That in
Although,
sky.
I mean, their quasar survey is, well, maybe still millions, actually.
Well, when looking at a sufficiently large number of things, you would expect that every once in a while you'd find a bunch of things aligned in perhaps a peculiar manner. I don't know if they proved that there was some causal thing that had aligned them, or if it was by chance, but
yeah, they thought it was, but I guess so. It was only a small fraction of the galactic nuclei that were aligned out of the whole. I thought it was like a lot of them altogether.
My understanding is that it was something like 20 nuclei that were fairly near each other were all aligned, which was unusual to say the least.
Could have been chance.
But again, we've seen hundreds of thousands of these objects, so
I see. Okay.
It's, again, my understanding is that it's improbable but a nifty thing we found.
Okay.
That it could have some cool implication, but I'm unfortunately not an expert in that area.
Actually, I hadn't heard about that before.
As to the supermassive black hole, I haven't read that paper, unfortunately. Did either of you guys? Any of you guys? So maybe the next panelists might know more.
Sure.
We could all go look at the stars if we're no more questions.
Sure.
They should still be out there.
What time is it?
Absolutely. It's